Right, it's a couple minutes after class, so I guess I should go ahead and get started. There's no one here yet, but that's okay. We are still pressing on with chapter 23. I'll probably be posting some more videos. I want to let everybody know initially, or right now, that I have decided to change the due date on I guess this will be the third online test, which is actually the fourth test total. But anyways, I had made it due like on the 16th, which is not this coming Sunday, but the Sunday thereafter. But I decided for my Monday, Wednesday classes, I'm just going to make it due Tuesday after you come back from spring break, so you have a little bit more time. And for my Tuesday, Thursday classes, I'm going to make it due for them on Wednesday, or excuse me, on Wednesday night, which is the 19th. So hopefully that'll help you guys. I've made the practice test as well as the other test open and available to those dates. If you find anything wrong with them, let me know. I always test them, but sometimes I find out that they don't necessarily import the way they're supposed to. So sometimes the banks that I know I have in the course don't necessarily link up with the tests that I make, the practice tests, the quizzes, the actual tests, the face-to-face tests, and it doesn't show the questions. So if anybody sees anything like that, please let me know. Again, I do prefer you to send me a text message to do that, but you can, of course, send me a email as well. Make sure you format your email properly, remember, with the proper subject line as spelled out in your syllabus. So when we last met, I spoke to you about how we're going to compute this new electric potential energy associated with electricity. And what we decided was that the general rule in general is using the change in potential energy is equal to the negative of the work done by a conservative force. So that sounds a little fishy, like it's not really fair, but that's why I pointed out last time that you can't really have a potential energy function unless you have a conservative force. So once you know that you have a force that's conservative, you can then immediately use the idea that the change in that the change in potential energy is equal to the negative of the work done by the conservative force. Once you do that, you can get a formula for it, and that's what we were able to do with ours. And in fact, what we ended up doing was we said that delta U was equal to the negative of the work done, and that negative of work done was negative integral of F dot dl, where F was the conservative force. In this case, we're talking about the Coulomb force. And then we went a little further and defined something called the electric potential. Notice I'm stopping short of the word energy because its units are not in energy, and it's not, the word energy is not used with it. So when we talk about potential or electric potential or voltage, we're talking about the same thing. And that's defined such that the change in electric potential or the change in potential or the change in voltage is equal to the change in potential energy divided by the charge Q. Therefore, when you go to calculate delta U equals the negative integral of F dot dl, where F is the conservative Coulomb force, when you're dividing it through by Q, you end up reducing the force, which is, since we know that the electric field is actually the force divided by the charge, then, or excuse me, the force is actually, yes, the electric field is actually the force divided by the charge. So we know that the integral becomes delta V, which equals delta U over Q, which equals the negative integral of E dot dl. Okay, so we're going to make use of that, and we're going to work some problems associated with that equation. So let's get started. I'm going to Jennifer, do you have any questions before we get started?
No, no,
Okay,
sorry, I was late.
that's cool. No problem. Like I said, it's not even necessarily required that you guys show up, so I don't mind just coming out here, and you never have to feel bad about being late. I tried to make it as late in the afternoon as possible so that people could access this if they had to work, because I thought that might have been the issue why people would even take 242 online. So hopefully it's late enough. But again, if it's not, that's not a big deal. I might even be able to move it back a little bit if that would help you guys. But right now I've got like 9 students in the class, and only two of you guys consistently show up. So if y'all want me to move it back, I can certainly do it, especially for you two. So let's get started. I'm going to go ahead and share my iPad screen. If you think of a question, just go ahead and blurt it out there, Jennifer. You can type it in the chat,
Okay.
and I may or may not see it, but you can. All right, here we go.
Okay.
Sharing my iPad. Maybe sharing my iPad screen. Okay. And I'm trying to make it look a little neater, so I started a little earlier this time and actually typed up the question a priori instead of just handwriting it on the fly. I like the handwriting because I'm working on trying to improve my handwriting, specifically cursive, of course. But anyways, it's more important that you guys are able to see it. So here's our first example. It says, and I would normally wouldn't word a question like this in a 241, 242 class, but I want to stress to you guys that this integral that we're doing for work is in fact what we would learn in a very advanced Calc 3 class that's called a that's called a line or path integral. So that's why I have the wording of the first 4 or 5 words here. It says use a path or line integral to compute the electric potential a distance r from the center of a charged conducting sphere of radius big R for r less than big R, B for r equal to big R, and C for r less than big R. Assume the total charge on the sphere is Q. So the one thing you got to notice from the very beginning here is I did say it was a conducting sphere. It has a radius big R, and the total charge is Q. And since it's a conducting sphere, that means that all the charge is going to remain on the outside edges. And of course, once you have that, you can use Gauss's law to draw a Gaussian surface just inside of the sphere, but inside of the actual charges. And since all the charges are on the outside and your Gaussian sphere is completely on the inside, the charge enclosed is zero. And since the charge enclosed is zero, that means the closed integral of E dot dl, or excuse me, E dot dA is also zero. So the electric field inside must be zero as well. So we're going to make use of that. And that is a static electricity situation. So let's begin. I'm going to start off with a solution. What we have is this equation right here that says delta V, which you can call VB minus VA, is equal to the negative integral from A to B of E dot dl. Okay, now that is specifically speaking a line or surface integral, and I've taught you, those of you who had me for 241, I taught you that it's important when you're doing this to use exactly one way to compute the integral and show which direction you're going. So, for instance, you can either use the dl and make it point in the direction that the integration is being carried out, and then if you do that, if you choose the DL to indicate the direction you're integrating, then the A to B just has to go in the positive coordinate direction of whatever coordinate you're changing in going from A to B. However, if you wish to do it the other way, then you can let A be the initial position and B be the final position, and then your DL just points in the positive coordinate direction for whichever coordinate again is changing and going from A to B. So that's sort of the big rule. What we have here is a sphere. I'm going to draw it in a coordinate system just so we'll have something to think about what's going on here. Whoa, that was weird. So let's do this. Let's do this. Okay, so this is our uh, coordinate system. This is my x-axis, this is my y-axis, and this is my z-axis. Not that that really matters very much. I am going to draw my sphere, and I am going to make it roughly 3 squares wide. So 1, 2, 3, and 1, 2, 3. So I'm trying to make these little red marks so that I can draw a circle and have the computer draw it more neatly by me trying to hit the dots. So let's go with this. Oops, I'm not going to do that one. Now I'm ready to roll. So I draw around here. You can see it got kind of bad there, but that's going to be our sphere. That's going to be the conducting sphere, and in fact, the radius of the conducting sphere is big R. And what I'm going to do is imagine going along a path, and the path I'm going to choose uh, is going to be some arbitrary direction But because this is a conservative force, the path that you choose doesn't matter. The end results will be the end results no matter what choice uh, you choose. So I'm going to imagine bringing it out from infinity where I can define the voltage to be zero. Because the electric potential, of course, depends on how close you are to the charge. And obviously, if you go infinitely far away and this thing's not infinitely large, you expect the voltage to be zero. So I can actually imagine integrating it, let's say, from way out here, which I will call R sub A, to way in here, which I will call R sub B, which is greater than R for this first part. Okay. So we do know that the electric field caused by a spherical charge distribution is actually given by Coulomb's law, and the Coulomb's law for the electric field is in fact E in magnitude is equal to Q over 4 pi epsilon naught R squared. And of course, it would point radially outward, assuming Q is positive. Of course, if you put in a negative number for the Q, then that would force the vectorness of it to turn to facing inward, which is exactly what you expect as well. So we're going to attempt to do this integral, and we're going to attempt to do it first for part A. So let me say part A is going to be, uh, we're going from delta V. We're going delta V is equal to VB, which is the final position, minus VA, which is the initial position. And the way I'm going to handle that is I'm going to pretend like it's RA and RB are finite distances, but then I'm going to take the limit as RA approaches infinity, and that will allow me to implement the voltage being zero at that point. And this is all going to be the integral from A to B of Q over 4 pi epsilon naught r squared. Now, that points in a radial direction, and the radial direction is defined by a nice little vector that I've told you guys about before. It's called r hat. And in fact, I can tell you exactly what r hat is if you wanted to. It's not that important to know it, but the way to think about it, and this is the part that you do need to know, is if you take any point in two or three dimensional space, it really doesn't matter, but any point in two or three dimensional space, if you draw a line back from that point in space into the origin, then you could draw a vector from that point to the origin, and that would point in the opposite direction of r hat. So if you flipped r hat away, then around 180 degrees, then you'd see that r hat actually points from, in terms of direction, not from location, but from the origin towards the point at which you wish to have the r hat vector. And of course, since it's a hat vector, it's 1 unit long. I am going to choose to let my range of integration dictate which direction or tell which direction we're going. So that means I'm just going to let the dl be dr r hat because that's in the positive coordinate direction. So I'm going to say dr r hat like that. Now what I can do is I can say the negative integral. And now in this case, since we've decided that we're going to let the limits of integration indicate which direction I'm integrating, then I just need to make sure the other one, the DL, just points in the positive coordinate direction, and I've done that. So now I'm going to write the integral from R sub A to R sub B of Q over 4 pi epsilon naught r squared r hat dot dr r hat. But the dot product, of course, is a linear operator, so we can pull the q over 4 pi epsilon naught r squared. We could actually pull that in between the dot and the dr if we wanted, but we could also pull the dr from between the dot and the r hat and to out in front, and that's actually what I'm going to do. I'm also going to pull out the constants, which are negative q over 4 pi epsilon naught. I pulled all that out in front. Now I'm integrating from RA to RB. And what we're going to integrate is dr times r hat dot r hat. But of course, r hat is a vector that is 1 unit long because of the hat. So you'd say it's the dot product is 1 times the cosine of the angle between them, but they're identical vectors, so the angle between them would be 0 degrees. And of course, cosine of 0 is 1. So we end up just getting r hat dot r hat is 1. The integral, oops, left off the r squared in the bottom. Notice I did pull out the 4 pi epsilon naught. I just left off the r squared in the bottom. But what we now have is an integral of r to the negative 2 power. And an integral of r to the negative 2 power is you actually add 1 to the exponent, so that'll become -1, and then you divide by the new exponent, which will be -1. So this is going to produce, which I'll write way over here just to conserve some space, because we're going to divide by -1, the negative in front of the q is going to become positive, so it's going to be q over 4 pi epsilon naught, and then we're going to get r to the -1 power, and then I've got to evaluate that from RA to RB, oops, to RB. But in doing so, I'm going to make the assumption that VA is equal to 0, and I'm going to take the limit as RA approaches infinity. So this becomes Q over 4 pi epsilon naught times 1 over RB minus. Now, here's the part where I do the limit. I'm going to take the limit as RA approaches infinity of 1 over RA, like that. And notice it is a scalar quantity we're getting now, but it also means this quantity right here goes to 0 as RA goes to infinity, because it just makes good common sense that when you're infinitely far away from something, the electric potential should be 0. So that's what we're doing here. Now, when we take the limit as RA approaches infinity of 1 over RA, that just becomes 0. So I'll put it like that. And we get the result is Q over 4 pi epsilon naught times RB, which in this case, we're actually going to let just RB be just the R less than, or excuse me, R bigger than big R. So I could call it RB, or I could call it just R, but the main reason, the main thing we're doing here is we're realizing that it is, in fact, a function of R. So the voltage at R greater than big R is, in fact, Q over 4 pi epsilon naught R. So that's our voltage for part A. And we should make a mention that basically delta V, since the VA became 0, delta V just became VB. And therefore, that's why I'm saying the voltage at R greater than big R is the voltage VB, which occurred at R equal RB, but we're now calling it just plain R. So hopefully that's not too confusing, but that's basically the result. The next part we have to deal with is for R equal to R. So what I'm going to say is for R equal to big R, we just get V at R equals big R just becomes Q over 4 pi epsilon naught big R. So, oops, and I really should have written that all in blue, except for maybe the words, but except for, yeah, the words I could leave green. That's not a problem. So let me go back and write it. So V at R equal big R is equal to Q over 4 pi epsilon naught big R, like that. And that's our answer for part B. Now we have to deal with R less than big R. So for R less than big R, we recall that E equals zero inside a conductor in electrostatics. That's what we're studying right now is electrostatics. So just to specify, that's really about like an electrostatic. But let me explain what I mean by electrostatic. So if I wanted to not have an electrostatic situation, for instance, I would connect a battery or some kind of power source to the actual conductor, and then that could actually establish an electric field in the conductor. But as long as we just got static charges and we can throw it on conductors and then wait for them to reach equilibrium and then look at it, that's static. That's electrostatic. So darn it, I hate it. This thing always turns into a eraser. So electrostatics. So since we know that, what we have is the ability to find the voltage from R equal big R to R equal little r that's less than big R. And the way we do that is, again, we use for part C, we're going to use delta V equals the VB minus VA equals the negative integral E dot DL. And in this case, this was supposed to be VB, and what we're doing is we're going to transform that into delta V equals just VB minus V at R. And that's equal to, of course, the negative integral of 0 dotted with dl because the electric field is 0, and therefore we just get 0. And what that means is that delta V is equal to VB minus VR so that we can find the new voltage VB, which equals the voltage at R less than big R. That's just equal to the voltage at R, which equals Q over 4 pi epsilon naught R. And that's actually the correct answer for part C. And in fact, we get an entirely different scenario than when we got earlier when we looked at the electric field. We had found, in fact, that the electric field, let me do it up here where I have some room. The electric field as a function of R for this very same type of configuration was Q over 4 pi epsilon naught R squared. That was at R, and what we found was it was there, and then it fell off like 1 over R squared. But then the electric field dropped to 0 and was here. That was for the electric field. Now the voltage is going to be quite a bit different in that the voltage looks like this. Again, we're going to have R being a critical point, and that would be Q over 4 pi epsilon naught big R. And what we get is a flat line, and then this falls off like 1 over R. So that's what the voltage plotted as a function of R looks like for this particular case, whereas the electric field, of course, was quite a bit different. Any questions on that one?
No.
Okay, that's cool. So yeah, it's a little complicated, but the big formula that you want to keep in mind is just that delta V equals basically this part. So that's what we use over and over again. But in most cases, you can just find the general formula, and that really is the formula. The voltage distance R away from a charge Q, if it's spherically symmetric, you're automatically going to have Q over 4 pi epsilon naught, or if it's just a point charge, it's automatically going to be Q over 4 pi epsilon naught. So, one, notice it is a scalar quantity, and two, notice that the strength of it falls off like 1 over r, whereas the strength of the electric field fell off like 1 over r squared, at least when you're dealing with point objects or large distances away from spherical charge distributions. Of course, remember we did a electric field for an infinitely long line charge, and that one fell off like 1 over r. And then we did a electric field for a infinite plane, and that one had no dependence whatsoever on distance. So it was as if the electric field was the same strength no matter how far away you got from it. But of course, that's more of a matter of calling something, or a result of calling something a infinite plane, when if it really was an infinite plane and you moved from, 1 meter away to 10 meters away, the infinite plane wouldn't look any different. Yeah, you'd have to walk a little bit further to get to it, but the ends would still look like they're infinitely far away above, below, left, and right of you. All right, let's move on to example two. It says when the electric field strength gets very high, even tried and true insulators break down and become conductors. For air, that breakdown electric field strength is about EBD. That means E breakdown uh, electric field is 3 times 10 to the 6 volts per meter, excuse me. A, show that the breakdown voltage VBD for a spherical conductor in air is proportional to the radius of the sphere. And B, estimate the breakdown voltage for a sphere of diameter 1.0 millimeters in air. So let's do that. I'm going to write solution. What I know here is that the electric field due to a particular spherical charge distribution or a point charge is in fact Q over 4 pi epsilon naught r squared. And what I know is the voltage is equal to Q over 4 pi epsilon naught r. Of course, the voltage being a scalar quantity and the electric field being a vector quantity. But the main thing we need to know here is E breakdown is equal to 3 times 10 to the 6 volts per meter. And last class, we discovered that all of a sudden we had a new unit for the electric field strength. Instead of newtons per coulomb, we can now use volts per meter. So that's what that is showing. All we have to do really is look at these two expressions, and what you'll see is that if you multiplied E by R, if you multiply E by R, then the magnitude of E would be equal to the magnitude of V. And therefore, if we choose specifically to think about to the radius of a particular sphere, which is what we're working on here, we'll change the R. Instead of it just being the generic R, it's going to be the generic R0 or something like that. So what we can see is that this V breakdown, which is the voltage analog to the electric field breakdown, you can actually get that by taking R0 and multiplying it by Q over 4 pi epsilon naught R0 squared, which is of course equal to R0 times E breakdown voltage. So that was what we were asked to show, was that the breakdown voltage is directly proportional to the radius. So in fact, it says show that the breakdown voltage VBD for a spherical conductor in air is proportional to the radius of the sphere. And we see that the breakdown voltage, which would be that 3 million volts per meter is just multiplied by R0 to get the breakdown voltage. Excuse me. I think in that sentence that I just said, I might have accidentally called the 3 times 10 to the 6 volts per meter the breakdown voltage. That's technically the breakdown electric field strength, not the breakdown voltage. But the breakdown voltage is clearly directly proportional uh, to the radius r. So now for part B, they want us to estimate the breakdown voltage for a sphere of diameter 1 millimeter. So for part B, oops, for part B, the breakdown voltage VBD is equal to, uh, since the diameter is 1 millimeter, it's going to be 0.50 millimeters is the radius. And of course, we can't use millimeters, so I have to multiply, I have to make this into meters. And of course, 1 meter is equal to 1,000 millimeters. So I do that, and then I multiply that by 3 times 10 to the 6 volts per meter. Now you can see that since we converted the millimeters to meters, we can see that the meters canceling out here, and that gives me, of course, zero point 0.5 times 3.6, 3 times 10 to the 6 is, of course, 1.5. Excuse me, writing the wrong color. That's equal to 1.5 times 10 to the 6 volts. So you can actually get a slightly smaller voltage, of course, than you expected from the electric field just by multiplying it by 1/2 by. So what that really means, by the way, is if you look at a lightning rod, you'll see the lightning rods are have a sharp tip. And that's what we're shooting for here. The sharp tip can be pictured as a part of a sphere, and of course, the smaller and smaller the diameter that sphere gets, the sharper and sharper the tip of that lightning rod gets. And that's what we're showing here. Is it turns out that as the radius of the tip of the lightning rod gets smaller and smaller, it allows the breakdown voltage to be reached easier and easier because it's actually a lower voltage than it would have been. In other words, you normally needed 3 million volts to go a meter, but if you make a tip of a lightning rod down to 0.5 millimeter, then you can actually just have a voltage of 1.5 million volts instead of 3 million volts, and that'll actually make it 1.5 million volts is big enough to actually cause the lightning from, or to cause the charge of the cloud to discharge through the lightning rod. So, if, by the way, if you happen to have a house with lightning rods on it, do not disconnect those big, thick iron wire thingies that are connected to it. You actually need those, or else your house is just a really big magnet for for pulling. Basically all the lightning strikes to your house and then setting it on fire, because without a path to ground, the lightning will just wreak havoc on your home. So, anyways, that's the answer to that. Any questions on that one, Jen?
No, but that's very interesting.
Isn't it kind of cool? Yeah, you do a more advanced introduction to this in like an electricity and magnetism course. I think we spent like a week and a half, 2 weeks in grad school on it, but we handled a much bigger problem and we used differential equations, but you get more or less the same result. So it is pretty interesting. Let's go on to example 3. Now, this one's a little bit weird, and I need to introduce something to you that you might not have realized yet, even though all the equations have been given to you. So it says how much work must be done to bring a charge Q equals 6 microcoulombs from infinity to a point 0.250 meters from a charge Q equal 35 microcoulombs. So we're really just talking about how can I pull charges from one place to another place and build an actual charge distribution. So when we do that, oops, sorry, I just realized something. Remember, I multiplied zero point 0.5 by 3 times 10 to the negative 6. I might have forgotten the 1,000. That was a little bit why I was hemming and hawing, because I thought the voltage would be considerably smaller, and it should have been, but I'm a crackhead, so I didn't even notice it. And I'm not really a crackhead, of course, but I'm just making fun of myself. So divided by 1,000, so this actually became 1.5 times 10 to the third volt. Sorry about that. I just remembered it as I was moving to the next page. Good thing I did. But notice now we needed, far as the electric field strength, we needed a voltage of 3 million volts for the lightning to strike just a distance of 1 meter. Now, what we found is that if you put a lightning rod up with a half a millimeter diameter point, then you only need a voltage of about 1,500 volts. And that would be enough to actually cause the discharge. And in fact, this is also, I forgot to tell you, did you ever see St. Elmo's fire? It's a Gen X type
Not in a
movie.
long time.
Yeah, that St. Elmo's fire, they're referring to St. Elmo's fire, and St. Elmo's fire is exactly coronal discharge that would occur on the mast of a ship, for instance, as a result of it being basically a lightning rod. So if you look out at a house, for instance, or a building like our campus at TCC, most of our buildings have lightning rods on it. If you look out in a cloudy night, you'll often see a little glow, a spherical glow around the tip of all the lightning rods, and that is what we call St. Elmo's fire. So, anyways, just thought I'd bring in that campy, I shouldn't say campy, but that Gen X type movie that was so influential to my life, along with, uh, 16 Candles, Pretty in Pink, Breakfast Club, all that good stuff. All right, so let's work this other problem. The main thing I have to tell you about this other problem is we need to look back at what I defined the change in potential energy to be. So the change in potential energy, delta U, which always delta means final minus initial unless we explicitly tell you otherwise. So I'm going to call it UB minus UA, and that was equal to the negative of the work done by the conservative force. So that would be the negative integral of F conservative dot dl. But we also define that to be delta V, uh, excuse me, we define that to be, yeah, excuse me, I will say it another way. I don't want to write it this way. So we've got that expression. But what we're going to do is we're going to say delta V is equal to VB minus VA, where again, final minus initial. And we're going to find that to be delta U over Q, which equals, of course, UB over Q minus UA over Q, which of course equals, like we said, VB over VA. So we can already see that the UB over Q is VB and the UA over Q is VA, but it's all equal to, if I divide that F by Q, I get electric field. So it's all equal to the electric field of the conservative force dotted with DL. Okay. Now that we have that, we can see that the change in potential energy is actually equal to Q times the change in electric potential. And that's the expression that I hadn't explicitly written out for you, even though I've written it, I just haven't boxed it off or said anything. This is also the origins of the new unit for energy that we're going to talk about. The new unit of energy is called the electron volt, and we'll talk about it in a second. So we're going to use that to actually compute exactly how much work it takes, because remember, the change in potential energy really is the work done in moving it, but specifically they call it the negative of the work done when it's done by the actual conservative force. So in this case, we're considering a different force doing it. So all we have to do to compute this is we calculate exactly what kind of force would be required, and we think about doing the integrals and stuff like that, but we don't have to because we've already worked it out for point charges. So what we're going to do is we're going to say that basically work done by some other force, and actually I should keep it in blue, sorry about that. The work done by some other force, some different external force, is actually equal to the change in potential energy. And that's, of course, equal to Q times the change in electric potential, which, of course, is the final minus the initial. So that's what we're going to use. But we happen to know what the VB is. So we can just go ahead and write Q. And then instead of VB, we can write Q over 4 pi epsilon naught r sub b minus q over 4 pi epsilon naught r sub a. So you could use Q there, and that would save you a lot of writing. It's just we very rarely use use K in real electrodynamics type calculations. So it's even though it is easier, it's just a little better and a little less formal, a little less foreign to me. So we're gonna do this, but in this case, we're actually imagining bringing this charge Q from infinity. So in fact, the initial positions at are A approaching infinity. So we can finally say that W is going to equal 6.00 times 10 to the negative 6 coulombs. And the negative 6, of course, is because it's micro coulombs that we found. And then we're going to take that and multiply it by the 35.0 times 10 to the negative 6 coulombs over 4 pi 8.85 times 10 to the negative 12th coulomb squared per Newton meter squared. You can actually express that in terms of volts and stuff as well, but we're supposed to bring that into a distance of 0.250 meters. So that's the first fraction, but the other fraction is going to be minus the limit as RA approaches infinity of dot 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 over RA. So what you see basically is this last part just goes to zero. I'm just not taking the time to show you all the details. So when we do this, we can say 6 times 10 to the negative 6 times 35 times 10 to the negative 6 divided by parentheses 4 times 3.14159 times 8.85 times 10 to the negative 12th times 0.250, and that gives me 7.55. Oops, wrong color. That gives me 7.5531. Again, going my practice of carrying two extra sig figs. And we only had three sig figs for all of these, so that three and the one's not a sig fig, but that turns out to be joules. And think about it, you're actually bringing a positive charge from infinitely far away from a positive charge. It should take a positive amount of work to move that 6 microcoulomb charge closer to that 35 microcoulomb charge. So you would expect a positive amount of work, and that's exactly what we got is a positive amount of work. Any question on that one?
No.
Okay, so that is the result. I'm going to go ahead and box it off. So we'll have the answer there. Didn't necessarily mean to make that W red, and the OCD has won again. So I'm filling it out. There's W. All right. So now that we've got that, I want to go on and show another beautiful thing about voltage. And this is a calculation that will now have done multiple times. And it's basically a calculation dealing with a electric dipole. So hopefully you remember I told you electric dipole is anytime you take two equal magnitude charges, one positive and one negative, and separate them. Excuse me, and separate them by a distance in space, and then they act as if they're tied together in some way. And as long as they're acting that way, then you can treat them like an electric dipole. So a case in point would be the water molecule, for instance. Uh, but let's go to example 4. It says calculate the potential A at a point 30 centimeters directly above the positive charge of an electric dipole, assuming the 30 centimeter distance is perpendicular to the dipole moment. And then B, repeat the calculation for a point 30 centimeters above the center of the electric dipole. The electric dipole is made up of one positive and one negative 50 microcoulomb charge, and they're 52.0 centimeters apart. So let's do solution. And I'm just going to draw the actual setup. So I'm going to start off by drawing a coordinate system just to make it nice and easy. So here's my coordinate system. And we really only need two dimensions in this case. So this one's going to be my x-axis. This one's going to be my y-axis. And I'm going to say that this is negative 20, or excuse me, this is positive 26.0 centimeters. And three spaces over here is negative 26.0 centimeters. And we are going to say that the positive charge is right here, and the negative charge will be right here. And of course, this charge is Q equals negative 50.0 microcoulombs, and this one is Q equals positive 50.0 microcoulombs. And now we'll go up to a distance of 30 centimeters. And that's going to be one of the places at which we wish to calculate the voltage. And the other one, the part A one, is directly above the positive charge right here. So this is the other spot. So I'll label this one step A, and I'll label this one step B, or points A and points B. So what we know here, because the math has been worked out, since this is 26 centimeters from the origin to the negative charge, and since it's 26 centimeters from the origin to the positive charge, then we happen to know that this distance, let me get a different color to mark this, this distance is 60 centimeters, and this distance is 40 centimeters. So that'll help us as well. So starting with part A, we want to compute the electric potential at point A. Now, electric potential, like I said, is a scalar quantity, so that makes it a lot easier. But the big point is we can say the voltage at A is equal to the voltage at A due to the positive charge plus the voltage at A due to the negative charge. That's all we have to do is just compute those. Now, the beautiful thing is these are scalars, so we don't have to break down into components. And this is actually a time where we use our formulas and we actually do put the signs in for the charges. So unlike when we use Coulomb's law for the force or Coulomb's law for the electric field, I told you you never want to put in the charges signs. In the case of voltage, you do. Okay, so just keep that in mind. The case of voltage, you've got to actually add the signs. So let's calculate the voltage at A due to the positive charge. That's going to be equal to what we found earlier was Q over 4 pi epsilon naught, and then times the distance between Q and A. So I'll say positive A like that. This, of course, is going to be positive 50.0 times 10 to the negative 6 coulombs divided by 4 pi times 8.85 times 10 to the negative 12th. I don't want to write the units because you can see I've already got problems here. But in this case, it's actually not too terribly bad because the distance, as you can tell from the diagram, from the positive charge to the point A is actually 30 centimeters. So I'm going to say 0.300 meters. Now, I did write that kind of small, but just in case, since I wrote it so small, I want to make sure everybody can see it. So I have 50 times 10 to the negative 6 coulombs. The units for the 8.85 times 10 to the negative 12th are coulombs squared per Newton meter squared. So you can see that the Newton and meter in the bottom, Newton meter squared in the bottom, the Newton will stay, but one of the meters will cancel. So that gives you a Newton meter in the bottom, which of course is a joule. And then the Coulomb on top, which we had Coulomb squared before. Now we have a Coulomb on top of a joule, which of course is sort of the very opposite of the voltage, which is supposed to be joules per coulomb. So hopefully that helps you. We're going to multiply this out. I'm going to say 50 times 10 to the negative 6 divided by parentheses 4 times 3.14159 times 8.85 times 10 to the negative 12 times zero point 0.3, close parentheses, and this gives me 1.4986. Now, I was only using 3 sig figs, but like always, I try to give a couple extra sig figs. So 1.4986 times 10 to the sixth. And this should actually give us volts because, again, a joule per coulomb is a volt. And what we had in the bottom was a joule in the bottom and a coulomb on top. So it was a coulomb per joule in the denominator, which becomes a joule per coulomb in the numerator. So that is our electric potential uh, in volts for the first charge. Now let's try the second charge. The second charge, or the second part, would be VA negative. So in doing that, I'm going to say VA negative is equal to Q over 4 pi epsilon naught, and this time it's A minus for the R. And this, of course, is equal to 50. In this case, it's negative, of course, so it's negative 50 times 10 to the negative 6 coulombs divided by 4 pi times 8.85 times 10 to the negative 12th coulombs squared per Newton meters squared. This time I went ahead and wrote the units in case y'all couldn't make out what I was saying earlier. And this time the distance is from the negative 50 microcoulombs to the point A. And in that case, the negative 50 to the point A is 60 centimeters. So I'm going to write 0.600 meters. And now I can work out the answer as negative 50 times 10 to the negative 6 divided by parentheses 4 times 3.14159 times 8.85 times 10 to the negative 12th times zero point 0.6, which you can see is pretty much the same calculation we did before, but twice as big in the denominator, so it should be half as big, which should be about 0.75 times 10 to the 6. When I do this calculation, I get negative 7.49. That's our 3 sig figs, and I'm just going to add the 3, 2, which are extra sig figs, and it's times 10 to the 1, 2, 3, 4, 5 times 10 to the fifth volts, which, as I said, is basically approximately 0.75 times 10 to the 6 volts. In other words, it really is about half as big as the last one. So now I can say that the voltage at A is 1.4986 minus 0.74932, and both of those are times 10 to the 6th volts, but you can see they're actually subtracting, and this gives us 1.4986 minus 0.7432 gives me 0.7554 times 10 to the 6th volts positive. And of course, we only had two decimal places on that, so these last two digits are not significant, and we've reduced our answer, in fact, to only two sig figs, so that VA is actually equal to, oops, let me make this A a little better. VA is actually equal to 7.554 times 10 to the fifth volts. And that's our first answer. Notice we didn't actually have to use the 6 coulomb charge at all because we're really, or excuse me, the oh, that's right. That was the other problem. Sorry about that. I was thinking we had used the six, but I was just looking at the 60 centimeters. Sorry about that. But anyways, that's the answer for part A. I think that should make some sense, but I think you probably can guess what the answer for part B is. Have you figured that out yet, Jen? Not to put you on the spot, but to put you on the
No,
spot.
no,
You're just surviving,
I'm
right?
hiding.
Gotcha. No problem. Well, for part B, we're going to say what we're supposed to do is VB, the total voltage at B, should be the voltage at B due to the positive charge plus the voltage at B due to the negative charge. The voltage at B due to the positive charge is going to be, again, notice this will be 50.0 times 10 to the negative 6 coulombs divided by 4 pi times epsilon naught times, in this case, notice by symmetry, you can tell the distance between point B and the negative, or excuse me, and the positive charge is also 40, so it's going to be 0.400 meters. And then when we do VB minus, that's going to be negative 50.0 times 10 to the negative 6 coulombs divided by 4 pi epsilon naught, again times 0.400 meters. Now we're going to add those two numbers together. Do you see what the two numbers are going to become? It's equal to positive dot 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 minus or plus negative dot dot dot, so it equals 0 volts. So that's the actual answer for part B, is at 0 volts. And that's just because these two formulas are completely identical, except one's got a negative charge on top and the other one's got a positive charge on top. Does that make sense, Jen?
Yes, it does. It doesn't help that my camera's not working. I'm sorry.
Oh yeah, that's right. You did tell me your camera wasn't working. I'm sorry, Jen.
You'd be able to see me writing otherwise.
Gotcha. All right. So your book then goes on and does some conceptual examples, which I highly recommend. I usually don't have the time to do the conceptual examples, so I want to make sure you continue to try to do those just to make sure you keep up your skills and learn the concepts. We just don't have as much time to do the concepts. We really need to spend more time on the solving problems because that's usually what gives students difficulty. So make sure you pay attention to those and like chapter opening questions, that sort of stuff, which I've told you all about before. Uh, Now, the thing that is left for us to deal with is the well, there's a couple things. One of the things is how can we, for instance, calculate the voltage for any kind of charge distribution? What if you have, for instance, 50 different charges? What happens then? Well, it turns out that again, voltage is a scalar quantity, so it's a lot less complicated than dealing with vectors. And we know that the formula for point charges is Q over 4 pi epsilon naught R. So what we have is V for a particular charge is just equal to Q over 4 pi epsilon naught R. So if you wanted the voltage, for instance, at a distance R away from a charge Q, this would be the formula for that. If you had multiple charges, then you could say V total would equal the summation from I equals 1 to n, where there's n charges, of course, of v sub I. So you'd have to make sure that you're all talking about the voltage at a particular point that we all agree on. So this is meaning that we're going to have to take the summation from I equals 1 to big N again of 1 over 4 pi epsilon naught. Notice that's common to each term, so we can actually pull that out in front of the summation. And then we're going to have a q sub I for the first charge. Obviously, that's q1. And then the distance would be r1 to the point A. So I should subscript this an A to recognize that we're doing it at a particular point A. And then the r would be the distance between charge I and point A. So that way we could do it and it would actually give us our total voltage. We just have to watch out because obviously sometimes when you're doing stuff like that, especially when you start to do the actual potential energy as opposed to the electric potential, then you have two charges, Q1 times Q I, and that two charges, you can end up repeating yourself by accident. So you got to watch out for that. But this is one good formula that we can make use of. So I'm going to go ahead and box it off. Of course, we already knew this one. Again, this is for voltage, a distance r from the center of a spherical charge distribution with total charge Q. So that's the voltage a distance r away from a charge Q that is spherically symmetric. Okay, so and it means specifically from the center, and then you can see obviously why the other formula came out to be what it is. But what if we want instead of a finite number of charges, what if we want a infinite number of charges? Well, it turns out that can be done pretty straightforwardly as well, and that formula is dV, the differential uh, chunk of voltage, if you will, is equal to dq over 4 pi epsilon naught r, which means, of course, that v, which equals the integral of dv, is equal to 1 over 4 pi epsilon naught times the integral of dq. And we have our normal setup where dq could equal rho dv or sigma dA or lambda dL. So that really is the important part of this, and now we can actually do the integration techniques that we had done before. This gets us a little closer because now we can do the same sort of problems that we were able to do earlier for the electric field using integrals. Now we can do it again for the electric potential using integrals, but of course a little bit easier because it doesn't have actual vectors associated with it. So let's look at an example. I'm going to go ahead and move to the next page to do the example, but what we're going to imagine is I'm going to start off drawing a coordinate system so you'll have some understanding of what we're dealing with, and I use a coordinate system that's a little different from what your book is choosing to use on a similar problem. But the reason why is I like to make use of coordinate systems and specific vectors within coordinate systems. So it makes it a little better when we do it my way. So here's the x-axis, here's the y-axis, and here's the z-axis. What I am going to do is imagine a charge distribution that is a hoop of charge. So a little hoop or ring of charge is what we're shooting for. I'm going to say I'm going to try to bring it in to roughly like this. So this is like that. And then, of course, this one would be roughly from here to here. And then this one would be like that. And that one, yep, that still turned out horrible. I don't like that at all. I really hate drawing. Anyways. All right, so let me try, see if the nice technique will work a little bit better when I'm using the software, and it does not appear. Oh, that looks, well, that's not horrible, but it's not perfect either. So that's supposed to be a ring of charge, and the radius of that ring, of course, is going to be capital R. So there's the radius, and what we're going to imagine is that there's a little chunk of charge dq that is out if you go out a distance or an angle theta counterclockwise from the positive x-axis as seen from the positive z-axis, and then you allow that angle to change by a small amount d theta, then that traces out a little chunk of the ring, and that little chunk of the ring is what we're going to call dq. This quantity right here is d theta, and this quantity, which is obviously a bit of arc length like we learned from trigonometry, so we know that S is equal to R times theta is at play. That means this quantity right here, which is dq, is going to be, we're going to assume again that it's a uniform charge distribution like we did before. It's a uniform charge distribution, which means that it has every centimeter of arc length has exactly the same amount of charge as every other centimeter. And in fact, every half centimeter has half as much charge, and every, you know, eighth of a centimeter has an eighth as much charge. That means that lambda, since this is a one-dimensional style object, lambda is a constant. So we're going to say dq is equal to lambda times dl, but dl is the arc length, so we have to call that r d theta. So that's what our dq is. And what we'd like to know is at this point up here on the axis, a distance z away, we'd like to know what is the voltage there. Okay, so we want to know what is the electric potential at that point above the center of the axis of symmetry, and I know that that circle that looks like an ellipse is not very well drawn, but you know it's supposed to just be a circle, and it looks elliptical because we're drawing it in 3 dimensions. So what I'm going to do is I'm going to say V equals the integral dV, which equals 1 over 4 pi epsilon naught times the integral of lambda times r times d theta. Now, I'm going to say lambda is equal to q over 2 pi r. And I'm also going to say that q, by saying that, I'm saying that lambda is a known quantity, and I'm saying that r is a known quantity, and I'm saying that big Q is a known quantity. Because of that, we should be able to figure out exactly what's going on. So there's my dq, and then I've got to divide it by r, the distance between the differential charge element dq and the point at which we wish to know the electric field. So you can imagine right about here is that distance. Now, remember that RD theta is a really small length, so where that green line hits isn't that big a deal. But the main thing to recognize is that the height is z, and the horizontal measurement, which lies in the xy plane, is r. So the length of this vector, and therefore the length of this r, I did call it a vector there, but the length of this distance is in fact r squared plus z squared, square root. Okay, so now I can go ahead and write, pulling this lambda and the r out in front, I'm going to say lambda, oops, I should be writing this in blue, not green. So I can say lambda r over 4 pi epsilon naught is equal to the integral from theta equals 0 to 2 pi of, now all I have is d theta divided by the square root of r squared plus z squared. Notice that integral does not depend at all on r squared or z squared, so we can pull those out as well. And what we're going to get is lambda times 2 pi r. The r was already there, and the integral from 0 to 2 pi is just 2 pi. And under it, we had 4 pi epsilon naught times the square root of r squared plus z squared, and that is the potential. Now, the reason why I left the 2 pi up there instead of canceling it out with the 4 pi is because that 2 pi r looks familiar. Hopefully, it looks familiar to you guys. It's specifically, uh, well, one way you could say it is specifically it is q over lambda. So if you multiply q over lambda times lambda, you just get q. So the voltage in terms of q is actually q over 4 pi epsilon naught square root r squared plus z squared, just like that. And that's our answer for our voltage above the middle. And that, of course, brings us to the next topic I wanted to cover, which specifically is there any way, now that we've done this neat little integral in such an easier way? Now, to be honest with you, when we did the Coulomb's law for this particular problem, that integral wasn't that bad. That wasn't as bad as the infinite line charge. But still, this is easier. And what I'm going to show you is, yes, there is a way that we can compute the actual electric field once we know the electric potential. And that's part of that litany of facts that I told you about in chapter 7 when we talked about conservative forces. Basically, if you find that a force is conservative, then the force has a curl that's identical to zero. That's one of the issues. Of course, if any one of these are true, all of them turn out to be true. So if you find the curl of a force is identically zero, meaning it's zero no matter what coordinates you plug in, then you have a conservative force. So there's a second stipulation, and there also that also means that if you calculate the work done by that conservative force from A to B, it will not depend on the path that's chosen. It will only depend on some function evaluated at B minus some function evaluated at A. And another condition is it turns out that any closed integral, any integral over a closed path of the work, in other words, the integral of f dot dl in a circle, is always going to be zero. And in fact, there's some other stuff too, one of which says there exists a scalar potential such that E, or in this case, or in the case of force, would be force is equal to the negative gradient of the potential. So that's what we're going to use now. We're going to say that based on that principle, E, the electric field, is equal to the negative gradient of V. Now remember, we could also say F is equal to the negative gradient of U, and that would work fine, but it turns out that we like working in the voltage world better than the potential energy world. Actually, to some extent, when Maxwell was making up his equations, he did a lot more with electric potential energy than we did, as opposed to electric potential, which is in volts. So it's not uncommon for people to at least think that maybe the potential energy is a better idea, but it's not very helpful. Now, what is this? What is this upside down triangle that you see? That's called the gradient. Okay, so del equals the gradient. That's another thing that we've been introduced to as a result of vector calculus. And specifically, for instance, you've probably heard of pressure gradients. You've probably heard your meteorologist, weatherman, or whatever talking about pressure gradients and stuff like that. That literally is a difference in pressure from one point to the other divided by the difference, the distance between the 2 points. So in some sense, you can see it's somewhat like a derivative because you're taking two functional values, pressure at one point minus pressure at another point and dividing it by the difference in the positions of those 2 points. So it looks like a slope and therefore it looks like a derivative. In fact, it's a vector quantity. So I'll put a vector symbol over all of it, even though you don't have to write the vector symbol over it. Some authors do, but you don't have to. And what it is we call it a operator, but basically to make it an operator and not look confusing, we have to write the unit vectors first. So you write I hat, and then you say the partial derivative with respect to x, and then you leave a space for whatever that gradient is put to the left of. So I leave a space, and then I say j hat, and we take the partial with respect to y. Again, we leave a space because the gradient is meant to be written to the left of something because it's operating to its right. So I leave a space again, and this becomes k hat partial with respect to z, again leaving a space to the side. So that's what the gradient is, and if it's operating on a scalar, which is what the electric potential is, then it just is a differential operator. So basically you're going to take the derivative of v. In the case of the first term, it's the derivative with respect to x, pretending like y and z are constants. In the second term, it's going to be with respect to y, pretending like x and z are constants. And in the third term, it's going to be with respect to z as if the x and y are constants. We're almost out of time, but that's good because we can use this now quickly to show you what the electric field would be for this, and you'll see that it agrees with what we calculated earlier in chapter 21 using Gauss's or using Coulomb's law. So the E is equal to the negative gradient of V, so that's going to be the negative. In this case, you can see that the vector function or the electric potential that we have in the red box above only depends on z. So the only part that's really relevant is going to be k hat times the partial with respect to z of q over 4 pi epsilon naught square root r squared plus z squared, which can be made a lot simpler as follows. I'm going to say negative q over 4 pi epsilon naught k hat times the partial with respect to z of r squared plus z squared to the negative 1/2 power. So when I take this derivative, I obviously am going to take the derivative of u to the negative 1/2 power, and that's going to be negative 1/2 times u to the negative 3/2. So the negative 1/2 comes out in front, and I'm going to get, in fact, positive q over 8 pi epsilon naught k hat, and that's just that part. Now I have the r squared plus z squared to the negative 3/2 because we have to take 2/2 from negative 1/2, so it'd be negative 1/2 minus 2/2 would be negative 3/2. And now we have to take the derivative of u with respect to z, and of course that is 2z. So that 2 is going to cancel out with the 2 that came in the bottom earlier, and what we're going to have is E is equal to Q. Whoa, all of a sudden it's starting to try to make a fancy drawing. So it's going to be QZ over 4 pi epsilon naught r squared plus z squared to the 3/2, which I think you can look and see that that is, in fact, exactly the electric field that we got when we calculated this with Coulomb's law. So, any questions on that one?
No.
Okay, we're out of time, so I'm gonna make a couple more videos just to finish off this chapter of 23 so we don't have it hanging over our head when we get back from spring break. Don't forget you do have spring break next week, and I announced at the beginning of this video just before you got here that I decided to push the next online test that was supposed to be due this Sunday I did push it back not only to the Sunday after spring break. I went ahead and went further for my Monday and Tuesday or Monday and Wednesday classes. I pushed it back to the Tuesday, which I think is the 18th maybe. And then for my Tuesday, Thursday classes like yours, I pushed it back to Wednesday, which is the 19th. So you can see the practice test and the online test are both available till then. And hopefully that helps you. But have a nice break. Stay
Yeah.
safe. Have a good time. And holler if you need anything.
Okay,
All
great.
right.
Thank you.
Thanks for coming, Jen.
Thank you. Bye.
Bye bye. All right. So I'm going to stop share. Now we've gotten taken care of. Still haven't finished chapter 23, just for the record. That was more or less like an example 23.9 that Giancoli had. There's example 23.10 that we can do, and that's probably one I'm going to make a video on. And then we've got to talk about equipotential lines and surfaces, which I mostly won't talk about in video. I'm just going to leave that for you guys to read. I'll talk about it face to face, that sort of thing as well. And then there's a potential due to electric dipole. We can calculate that rather quickly and maybe even do some examples associated with it. But we're essentially completed with chapter 23, other than a couple of examples. So thanks for coming, everybody. Have a good evening, and bye bye.